So let us discuss the solutions for assignment 6. In the first question, we are given an equation for a logic gate, and we are asked to find out what are the size of the NMOS and PMOS connected to the input C. So ABC, the whole bar, it's fairly straightforward. It's a NAND gate, right? So A, B, C, that makes the N stack. Let's say it's like this: A, B, C. This is a 3 stack, so it's sized up as 3 because each one is R by 3, right? Each one is R by 3, so totally the resistance is R, because size 1 corresponds to resistance of unity. And of course, now we have to make the dual stack on the PMOS. Since this is not a self-dual function, you'll have to implement the dual stack as is, but it's okay because the stack size of the PMOS is just 1. So that means you can just get away with a single transistor for the PMOS. 3 transistors of them in parallel. So the size of the NMOS is 3 and the size of the PMOS is 2. So it's 3, 2. This is the answer. Next, moving to question number 2. Similarly, again, we are given a logic equation and asked to find out how to implement this. So if you look at the size of the NMOS connected to input D, right? So let's just look at the N stack of this. So we have A, B, C, right? Product terms A, B, and C, and then that is ORed with D, and the whole thing is produced with E, right? So this is the implementation that takes the minimum number of transistors, because if I were to put that E inside, then it would become one E here and another E here. That is, if I were to distribute the E inside this bracket, right? But no, I'm not going to do that because I've said it required the minimum number of transistors. Right? So now first we find the size of the stack. The size of the stack is the longest chain of transistors. That's 4, right? So that means each one should have a size of 4 in the stack, right? So we just need to find out what the size of the NMOS is here. So what is the resistance? We want the resistance down this path to be R, right? We want resistance down our paths to be R. So if this is 4, how big can you make that transistor? If this is 4, what is its resistance? R by 4. Why? Because unit width corresponds to a resistance of R. So the question is, width 4 corresponds to what? Right? And we know that resistance is inversely proportional to width. So R is equal to K times unit width, right? So let's say R1 corresponds to K times 4 unit width. This is 1 by 4 times K by unit width. So this is 1 by 4 times this one. K by WU is R, 1 by 4 times R. So this 4 corresponds to, so what I'm saying is WU unit width is 1, right? So 1 by 4R is the resistance here, right? 1 by 4R. So you can allow this to be 3 by 4R. So R divided by 4 by 3 or 3 by 4R. And so that means the width here is going to be 4 by 3. So yeah, 4 by 3 is the answer here. Right, because again R divided by 4 by 3. So R is K divided by WU into 4 by 3. Right, R is equal to K by WU. Why? Because R is inversely proportional to WU is to the width. So the K is the constant of proportionality. So I just substitute for R there, and so that means the width is, so if R1 is equal to this guy, that means this would have to be the, it would mean that this is the width over here, because this is the constant of proportionality, right? So yeah, in question 3, again we are now given we are given some circuit logic, a circuit for this logic gate, and asked to find out what equation it's implementing. So let's look at it from the N stack, and we see that there are two of them in series, and that series stack is parallel with this other stack, right, by this common connection, right? So the two guys in series have input A and input C, and the other guy has input B. So because A and C are in series in the N stack, it's AC, and because B is in parallel with the AC stack, it would be odd. And since it's the CMOS inverter, we will take the complement, right? Since we are looking at the what is implemented on the N stack, it is complement. So the answer is AC plus B the whole bar. So just for the sake of correctness, we should also check whether the PMOS stack implements the dual. So A and C are in series here, A and C are in parallel here, right? AC stack is in parallel with the B stack, AC stack is in series with the B stack. So it's all correct. Now we are given that there is a logic gate whose logical effort is G, whose electrical effort is H, parasitic effort is P, for the size 1 logic gate. The next 3 questions will be about what happens to the logical, electrical and parasitic efforts as the gate sizes are increased. So in a size 4 logical, in a size 4 gate, the logical effort is exactly the same as a size 1 gate, because the logical effort does not change with sizing. And this is because, so if you take a inverter, let's say for example, but this argument generalizes to other logic gates too. If you take an inverter and you do 4 2, that means the resistance here is now R by 2. The resistance here is now R by 2, because equal rise and fall delay. So that means now to calculate the logical effort, so it sinks a current of 2I. So to calculate the logical effort, you would have to take it against, you can't anymore compare it with the 2-1 inverter, right? Because this has R and this has R. So you would have to compare it with the same resistance gate on the stacks, right? So you would have to compare it with a guy with the same resistance, R by 2 here, R by 2 here. That's 4 and 2. So the gate cap here CG is equal to CG2 is equal to 6 and CG1 is equal to 6. So yeah, the logical effort is CG1 by CG2. This is the reference gate and this is the gate we are looking to find the logical effort for. CG1 by CG2, that's 6 by 6 and it's 1. So for a size 1 inverter, the logical effort was 1. For a size 2 inverter also, this is a size 2 inverter, right? Because all the transistors are doubled in width as compared to the reference, size, as compared to the size 1 inverter, not reference inverter, as compared to the size 1 inverter. And so therefore, you're seeing that the logical effort still does not change. It's still 1. Even for a size 1 inverter, the logical effort is 1. So therefore, if the logical effort is now equal to the old logical effort, this is 1 times the old logical effort. So K is 1. And now what is the electrical effort? Now in the case of the electrical effort, the load doesn't change. So electrical effort H is just going to be C load by C gate. Right. And now if you make C gate as 4 C gate, the new electrical effort is going to be C load by 4 C gate, right? If you've now made it 4 times. So that's just 1 by 4 C load by C gate, which is, as you can already see, H by 4. So it's 0.25 H. K is 0.25. Then and finally the parasitic effort. The parasitic effort for arguments similar to the logical effort also does not change with size, right? Because again, you would have to compare it. Actually, no, it's a different argument to the one made by the logical effort. So in the parasitic, so the idea with the parasitic effort is, all you're trying to do is figure out what the resistance of the stack is, right, into the parasitic capacitance. This is what the parasitic effort ultimately finds out, right? So now if you were to size up the stack, let's say by 4 by n times, right, then resistance goes 1 by n, because resistance is inversely proportional to width. You increase the width n times, so resistance goes 1 by n. But then the capacitance is directly proportional to the width. So C parasitic will now become into n. So these two will cancel out and you will find that the delay corresponding to that does not change. So yeah, it's just it doesn't change with the size. So the answer is 1. K is equal to 1. In question 7, the total diffusion capacitance on the output port of a NOR gate is, so let's look at a NOR 4 gate. We have so it's A plus B plus C plus D the whole bar, NOR 4. So on the N stack, it's fairly straightforward. It's 1, 2, 3, 4 NMOSes in parallel, right? And they all have size 1 each. We will use a different color for that. But on the P side, now since it's the dual, these will all be in series. So that means now it's a 4 stack, and actually you would have to do 4x the unit width is 2, so that's 8. So essentially it is the amount of parasitic cap here would be 8 plus 1 plus 1 plus 1 plus 1, right? This guy, this guy, this guy, this guy, and this guy would contribute to the parasitic cap on that node. So this is 8 plus 4, which is 12. And that's the answer. Similarly, we are asked the diffusion capacitance, the output of a NAND 4 gate. NAND 4 gate, it's A, B, C, D, the whole bar. So on the N side, you have this, right? A, B, C, D. This is on the NMOS side. And on the PMOS side, you have this. Right? A, B, C, D. So now the stack size for the NMOS is 4 because it's a 4 stack. The transistor width is now has to be 4 times the unit width because it's a 4 stack, and it's a 1 stack on the PMOSes, so you just take the unit width, which is 2. Right? So now we calculate the parasitic capacitance in the exact same way. The parasitic capacitance here is going to be this guy, this guy, this guy, this guy, and this guy. So it's 4 plus 2 plus 2 plus 2 plus 2. It's 4 plus 8, which is equal to 12. Question 9. In the logic gate from question 2. So I think question 2's logic gate was A, B, C times D plus E the whole bar, if I'm not wrong. Yes. So I think let's copy that figure. So we are asked what the capacitance that corresponds to the input node D is, right? So we are asked, so the input node is this guy. So it goes to an NMOS and a PMOS. What is the capacitance at that node? So to do that, let us complete the figure. Maybe I'll take it to a different here and change the background. Right? So we are asked what the capacitance at that node is, and for that, let us complete the figure. We have the E, right, which is in series, so it should now become in parallel. So in parallel to E, we have, and it goes to VDD, of course, we have the this guy in series. These two are in parallel, so now they'll become in series. So that's D. So I'll just connect that there. That's D. I haven't given the sizes yet because I have to work it out. So, and therefore these guys are in series, so they become in parallel. So that's A, B, and C. So now let's work out the sizes. This is it's a 2 stack, right? So that means you have a size of This is a one stack, so therefore you can just use 2 over here, and you can just use 2 here, and but this is a 2 stack, so you would have to use 4, 4, 4 and 4. So it's the capacitance over here is 4C, the capacitance over here is 4 by 3C. So we get 4C plus 4 by 3C, which is equal to 16 by 3C. Right? If you work that out, that will come out to 16 by 3. And that's the answer. In question 10, the total diffusion capacitance on the output node of a size 1 equal rise and fall delay inverter NAND 4 gate is 36 femtofarads, right? So let's draw it again. 1, 2, 3, 4. This is NAND 4 gate. Yeah, so A, B, C, D. This is the output node Y, and it has a capacitance of 36 femtofarad. This is the total parasitic capacitance here, diffusion capacitance here. Now we are asked to find out what the diffusion capacitance on the output node of a size 1 inverter with equal rise and fall delay. Remember, so this says size 1 NAND 4 gate. So all the sizes here will be unit sized. So for unit size NAND 4 gate, it's 4, 4, 4, 4, 2, 2, 2, 2. So the total cap here is going to be 12C. 12C is equal to 36 femtofarad. That means C is equal to 3 femtofarad. And so now for the output node of a size 1 inverter, we will get this 2, 1, right? Size 1 inverter. So this is 2 plus 1, 3C. When you look at it like that, 3C corresponds to 9 femtofarad. The answer is 9. And it's the same way for the NOR gate. You go to the NOR gate and you find out its capacitance, right? So the NOR gate, I'll just draw the output nodes, right? So it's 1, 2, and 3. This is the N stack, and I'll only draw 1 on the PMOS, but you should remember that that's a 3 stack. So this is 2 times 3, that's 6, because it's a 3 stack. So that's 1, 1, and 1. So this is the capacitance here is going to be 6 plus 1 plus 1 plus 1, right? These guys times C. So that's 9C, right? 9C corresponds to 27 femtofarad. Similarly, now we get C is equal to 3 femtofarad. And the diffusion cap of the intermediate node between any two PMOS transistors, right? So now we will look at the P stack as well, right? So we are saying that this is the P stack, and we are asked to find what the diffusion capacitance on the intermediate node is, right? So if you remember in class, sir would have said that if there are two nodes and they are the only two nodes that are sharing that, then you can actually share the diffusions. It can become a single diffusion, and so therefore you get only a single diffusion cap. You get the diffusion cap only worth one of these guys. So that will be 6C, right? C is 3 femtofarad, so this is 18 femtofarad, and that is the answer because of shared diffusion. So in question 12, in a static CMOS implementation, the PMOS transistor network should be used as the following. Pull down the output to ground? No. Pull up the output to VDD? Of course. CMOS circuit is made up of only NMOS transistors? No. And none of the above is obviously not there because it is one of the above. The PMOS stack of a NOR 5 gate has a stack of size what? So NOR 4 gate, I believe I drew a NOR 4 gate here. So in a NOR 5 gate, you'll just have one more guy in the P stack and you'll have one more NMOS in parallel. So if you have one more guy in a 4 stack, it's a 5 stack. In series, if you have one more guy in a 4 stack, it's a 5 stack. So a NOR 5 gate has a stack of size 5, right? So in question 14, the answer is 2 actually. What is the size of the PMOS stack required to implement this function? So if you notice, this function just corresponds to AB plus BC plus AC, the whole bar, right? Because this function for will go to 1 for the minterm 0, which corresponds to A, B, C being 0, 0, 0, right? It will go for 1, 0, 0, 1. It will go for 2, 0, 1, 0. Because if any 2 or 0, if there are two zeros, then two of these terms will, for example, if A and C are 0, then A occurs in two terms and B also occurs in two different terms. So two variables are enough actually to capture all the terms in this summation. So if two variables are 0, then the whole thing becomes 0, right? The whole thing becomes 1. I mean, the sum becomes 0, the complement of that becomes 1, right? So, and finally, the only other combination where there are two zeros is 4, right? 1, 0, 0, right? And if you notice, this is, I'm sure sir would have said this function, that it's possible if the function is a self-dual function as in if f is equal to f dual, to implement the function, if it's possible if it's a self-dual function to implement it quite minimally, right? You can just mirror, both stacks will be mirror images of each other, so whichever stack requires the lesser size implementation, you can just use that and mirror it on the other stack. Quite clearly over here, the N stack only requires the NMOS side of the network requires only a 2 stack to implement this, because this will simply be AB plus BC plus AC, right? This is the N stack. That's AB plus BC plus CA, right? So this will be the N stack, and you can simply mirror this as so, right? AB, BC and AC. Right? So the why can you do this? Because f is a self-dual function. You can try it out, right? You will find that if you take the dual of this function, right, you will get back the same function. And another way to check if a function is dual is if you were to complement all the terms, right? If you were to complement all the min terms, so let's just do the truth table. So for all these guys it's 1, and for the remaining guys it's 0, 1, 2, 3, 4. So let's say I complemented 0, 0, 0. So I get 1, 1, 1. The output is also complemented. 1 becomes 0. Similarly, I complement 0, 0, 1, right? So let's say this is now 0, 1, 0. The output is complemented, right? And it's not that I'm just filling these entries here. These are the actual entries of the truth table. 0, 1, 1, right? Two of them are 1, so therefore two terms will become, there'll be a term over here that becomes 1, so therefore the complement of that will become 0, and you have 1, 1, 0, right? So for every term here that is 1, you have a term here which is the complement of its bits, exact complement, bitwise complement, and whose output is also a complement, right? For 0, 0, 1 you have 1, 1, 0, right? 1 to 0, that's complemented. For 0, 1, 0, actually this is not 0, 1, 0, this would probably be 1, 0, 1, not 0, 1, 0, 1, 0, 1. So for 0, 1, 0 you have 1, 0, 1, right? And for 1, 0, 0 you have 0, 1, 1. So this is a way to check if it's a self-dual function. If it's a self-dual function, what you will get is f of a complement, b complement, c complement is f complement of a, b, c. So if you complement the bits, the value itself gets complemented, right? So that's a check for a that's one of the checks for a self-dual function. Another thing is you can just actually take the dual of the expression and work it out. You'll find that you'll get the same expression back. So yeah, that's question 14. In question 15, what is the size of the NMOS stack in the logic gate from question 2, right? So yeah, for the question 2, we have this, and this is question 2, and this is the N stack for it, and this is of course 4 stack. So the size of the N stack is 4, right? So that's 4. In question 16, the sum of the widths of the PMOS transistor so that the worst case pull up and pull down resistance is identical to that of the reference CMOS inverter is what, right? So yeah, we just have to mirror this properly. I'm sorry, we just have to dual it and get the N stack properly. So you have A, right? So A is in parallel with this, so it will become in series with that. And what is that? It is the B is in series with this, so it will become in parallel with that. So this A and this B is now in parallel with something, and these two guys are in parallel, so they now become in series. So that's C and D, right? And now this is a 3 stack, right? That's 3 transistors. So you would take 3, 3, 3. So this has a resistance of R by 3. So you need a resistance of 2R by 3 here, so as to be able to get a total resistance of 3 on this, of R on this. So that means you can just use 3 by 2. You can check that 3 by 2 will give resistance of, width of 3 by 2 gives resistance of 2R by 3 if unit width gives resistance of R. Right, so now we just add all these. So that was the N stack, but the question asks us to find the sum of the widths of the PMOS transistors, right? So that the worst case pull up and pull down resistance is identical. We can do similar sizing. Actually over here there's no question of sizing ambiguity. So it's just 2 here, and these are just 4 stacks or 2 stacks, so that becomes 4, 4 and 4. So that is 4 3s are 12 plus 2, 14, right? So the answer is 14. And yeah, so for some of the widths of the NMOS transistors for the same circuit will be 10.5. Why? Because of this. right? So that's 3 plus 3 plus 3 is 9, plus 3, 3 by 2 is 1.5, so 9 plus 1.5 is 10.5. So this is 10.5.